So I've got handy the review sheet I gave y'all last week and then also the PowerPoint slides. So I hope I can kind of make sense of this. The test isn't made out, but I see on the review sheet general structure and parts of an atom. So generally know that this is what an atom looks like. And we have in the middle, it's called the nucleus. We have protons and neutrons. And then in the cloud outside, we have the electrons. And then I also have atomic number. Atomic number is the number of protons in the nucleus, and actually that gives the chemical identity of the element of that atom. So that's pretty cool. Mass number is the number, I don't see it on here, but mass number is equal to number of protons plus number of neutrons. So mass number is always going to be an integer. You count protons plus neutrons. Let's see. Then I have classification of matter. So several times you had this. Of course, matter can either be a pure substance or a mixture. If it's a pure substance, you're looking at either an element or compound. If it's a mixture, it can be well mixed. We call it homogeneous, or if it's chunky, we call it heterogeneous. All right, and I have models of the atom over time. So I could probably multiple choice question, I think, I'm not sure. This is what we knew about an atom. So we know that all matter is made of atoms, and then we came along with the thought, well, there are positively and negatively charged pieces in an atom. And then this one with Rutherford, this is where we have the nucleus with the protons and the neutrons and the electron cloud outside. Bohr said the electrons kind of have these kind of energy levels. Electrons can be here, a lower level or a high level. And then Schrodinger kind of picked up where Bohr left off and said that actually electrons, it's kind of a Heisenberg's uncertainty thing principle. We can't really know where they are. They're kind of in a cloud like that. Then I've got electrons creating absorption lines. So one of the things is, and the reason I'm covering this is because when we talk in astronomy, these would be like fingerprints of stars with a surface temperature of 3,000 Kelvin, a star with a 4,000 Kelvin surface temperature. Heaven forbid a hot star with a surface temperature of 30,000 Kelvin. And if we get back these lines from the star, so you can kind of see those dark lines, that's an indication of what element they are. So for instance, we have hydrogen and helium, carbon, iron, oxygen, magnesium, sodium, oxygen, titanium oxide, carbon, hydrogen molecule. So these spectral lines come from electrons. Okay, what else do you need to know? So we have absorption lines. So these dark lines are absorption lines. Okay, dark lines are absorption lines. And that is actually, if this is the nucleus, I'll put N for nucleus. Oops, maybe I have a better picture coming up. If that's the nucleus, and this is an energy level, energy level, energy level, the dark lines are created as electrons are being excited and going up. That gives you dark. Okay, and the bright lines are created as they're going from a high to a lower energy. They're giving up energy, so that gives you bright. So however you want to kind of get that figured out. So this is kind of what I was talking about. So this would be the nucleus with the neutrons and protons, and this is where the electrons can reside. These are different energy levels. So this is N is equal to 1, 2, 3, 4. So the electrons can be there. So let's see, what do you need to know for your test? I think that might be it. All right. And it's all about the electrons. The phenomenon of fireworks actually are electrons transitioning between actually going from a higher to a lower energy level. And our northern lights are also created as by the same phenomenon. Then I have electron cloud. So this is Schrodinger's model that says electrons are actually kind of buzzing around. You can't actually pin them down. They're in a cloud. And then Heisenberg's uncertainty principle, it simply says that you can't know the exact location and energy of an electron. So things that are small on a very, very, very small scale like electrons, they can kind of fit into this Heisenberg uncertainty principle. All right, excuse me. I go to part 2, periodic table. So, excuse me. You need to know your groups. So of course this is a group, these are groups, okay, and this isn't a very good periodic table to give you an example of. The periodic table you have has this, 1A, you know, 2A, then we skip the B's and we go 3A, 4A. These are the main group elements all the way to 8A. Okay, so those are groups. Periods go across this way. Those are periods. So this is period 1, 2, 3, 4, 5. It goes like this, all right? Let's see. Similar elements with, and so it's up and down, that these guys are going to have similar similarity with regard to how they react. Chunking up the periodic table. Okay, so maybe this is all what I kind of did a minute ago. So here's my 1A through 8A. So chunking up the periodic table. So you're going to want to know the names for these first two, alkali metals and alkaline earth metals. You're going to want to know the name for these last two, noble gases and halogens. You're going to need to know, and it's not, see if it's on, yeah, this one, you're going to need to know this JAG. This separates metals from nonmetals. And then you're going to need to know, these are the transition elements. I think that's about it. Oh, sorry. Well, these are the inner transition elements, and these are the transition elements. Sorry. I'll put M, and this is transition. So kind of know that. Review it if you need to. Let's see. Next one. Oh, yeah. So look these up on your periodic table and know that these are the number of protons in the nuclei of the element. So these are the atomic numbers, and be able to match the symbol with a name for those. Valence electrons. You get the number of valence electrons from the group number. So of course the periodic table is kind of split here, and we have our group B elements. But 1A has 1 valence electron, 5A has 5 valence electrons, 7A has 7 valence electrons. So you're going to want to know that. And I'm not going to mess with any of the B's, just all the A, the valence electrons you can pick off of the period, of the group number. Let's see, top abundance of elements. So I have 3 slides here. This is the universe. Of course, most of the universe is hydrogen. This is the Earth's crust. Most of the Earth's crust is oxygen. And this is the human body. And most of the human body is also oxygen. Then I've got characteristics of electrons, protons, and neutrons. So electrons are negatively charged. They're generally massless, and they're in a cloud around the nucleus. Protons are positively charged. They weigh about 1 U. And the protons are the atomic number, and they give the element its identity. Neutrons help the protons kind of what we say coexist, and they also weigh about 1 U, and they are neutrally charged. They're also located in the nucleus along with the protons. Isotopes. I have isotopes counting protons and neutrons given mass number. So I think that other part's coming. But what is an isotope? An isotope is of the same element, so it has the same number of protons, but it has a different number of neutrons. Where it is. There it is. Neutrons differ. Okay, and then you know you have an isotopes of each other. All right, yeah, I have here, oops, back, previous. Counting protons and neutrons given mass number. So, for instance, oh, I don't have a periodic table. Yeah, I do. So, for instance, if we pick on calcium, this is the mass number. And remember what the mass number is. It's the number of protons plus the number of neutrons. And I have a periodic table here. I can look up calcium. Calcium is a 2A element, and it's got 20. It's 20 protons because it's atomic number 20. So if it's got 20 protons and the mass number is 44, can you see where the neutrons is 44 minus 20 equals 24? Does that make sense? So that's how you would get, given the mass number, you can get to the number of neutrons. Well, the number of protons is given by the symbol or the element it is. So here I have formation of ions. It says metals lose electrons, form cations, nonmetals gain electrons, form anions. So let's see, what do we got here? I'm not gonna worry about here. I'm gonna look at this. So the metals will generally form cations. And 1A, remember that group I told you to put a 1 plus 1. 2A told you to top of that, I said you put plus 2. 3A said beginning with aluminum to put plus 3. So they will lose an electron. And the nonmetals will pick up an electron, form negatively charged anions. And this is what I told you to put up the group, top of the group. A -1 for 7A, a -2 for 6A, excuse me, a -3 for 5A. All right. So then I have used position in periodic table to know which element will form. That goes back to this one. So for instance, pick on these 7A. Let's see what I'd say down here. 7A, those fluorine and chlorine are going to form a -1 charge because you're going to have a -1 at the top there. Let's see, -1, -2, -3, +1, +2, +3. All right. From shorthand notation, knock out the atomic number, the mass number, number of protons, number of neutrons, and number of electrons. So all of this information came from this. Its atomic number is 9. Atomic number, if it's given, doesn't always have to be given. It's going to be in the lower left-hand corner. We can get the atomic number from looking at the periodic table and finding it, fluorine. Its mass number, the big number here, remember that's the neutrons plus the protons. So protons are 9 because that's atomic number. Electrons are 9 because it's neutral, there's no charge up here. And neutrons, we got that by taking 19, the mass number, and from that subtracting the number of protons to get 10 neutrons. So now here's a cation. This is one of our metals giving up electrons to form cations. So the thing that's different is it has 20 protons. The thing that's different is the electrons. Okay, the electrons, I think that's supposed to go up there. The fact that it actually, if it was neutral, look at it this way. Since it has 20 protons, if it was neutral, it would have 20 electrons, okay? But it's a +2, so that means it has 2 less electrons. Okay, -18, and that's where this 18 came from. Number of neutrons came from taking the mass number, 39, and from that subtracting the number of protons, okay, to give you 19. So I hope that helps. And then the nonmetals like chlorine form anions. So in the case of 7A elements, it's going to pick up an electron, become a -1 charge. So now for the electrons, if it was neutral, it would have, this is protons, if neutral it would have 17 protons, but since it's -1, it has actually picked up 1 electron, so it actually has 17 plus 1 equals 18 electrons. So that's where this number comes in. Number of neutrons we get from difference by taking 36 minus 17, and that will give you 19. So number of protons plus neutrons minus the number of protons will give you neutrons. That's where that is. All right, part 3. 2 types of compounds, ionic, molecular. So generally no, there's 2 types of compounds, ionic, molecular. And actually I think it probably took a little bit of time saying what's different about them. Molecular compounds are called molecules, ionic compounds are called formula unit. If you have a metal there, then you must have an ionic compound. If they're all nonmetals, it's a molecular compound. In the case of that, we're talking about hydrogens being a nonmetal. All right. Ionic versus molecular bonds. Maybe that's coming up. I don't know. Make a little note there. The compound's mass. This one isn't too bad. I wonder if I skipped a bunch. Okay, so to get how much a compound weighs, you just simply add. I'm just going to put add. You're going to add up. You're going to use the periodic table, and if you have 2 hydrogens, you're going to take 2 times whatever hydrogen weighs plus oxygen, 1 times oxygen for water, that sort of thing. Okay, so this is going back to ionic versus molecular bonds. So How's this go? Shared. Okay, shared are molecular bonds. And ionic bonds are when electrons are transferred. Okay. Let's see. Electronegativity. The symbol for electronegativity is this X-looking thing. And electronegativity increases as you go from left to right, group A elements anyway, and it increases as you go from bottom up. Okay, so increases. So that makes our nonmetals most electronegative. And what electronegativity is that they are attracting more electrons to themselves. That was that discussion. This might be a vocab word. I haven't decided yet. But if electrons are shared, so this is E shared, electrons shared, which of course is a type of covalent or molecular bond, but if they aren't shared equally, so you kind of have this sort of, you have something that is partially negative and something that is partially positive, shared unequally, that makes the bond polar. Seems like I just did this one. I just did that one too. Wow. All right. So Lewis structure. You need to be able to add up. I hope I have it. I see I missed one. Hopefully simple binary ionic compounds. So for Lewis structures, you need to be able to come up with a pot of valence electrons. And actually that's related to, remember, you know the valence electrons from the group number. Okay. So for instance, let's see, H2O. I think I probably did this one. Hydrogens have one valence electron, and oxygens, just because hydrogens only have one electron and it is valence. Oxygen is in 6A group, and so it actually has 6 valence electrons. So what we do is we take 2 times 1. So for hydrogen, you're looking at a total of 2, and we take 1 times 6. So we have 8 valence electrons there. That's the pot of valence electrons. And then on our Lewis structures, remember we're going to see single bonds, double bonds, and triple bonds. Single are 2 electrons, double are 4 electrons, and triple bonds are 6 electrons from our pot. If you see a dot dot, that's lone pair electrons, and they don't bond to anything, but they're important. They're part of the pot, and they give shape around that atom. Let's see. I don't know. I feel like I'm missing something, but I tried. Let's see. So, for instance, then, if you're given this, and you're supposed to count the pot of electrons, excuse me, on that Lewis structure, I have 2, 4, 6, 8, and this is 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. And I have 30, 32, 34, 36. So I get 36 electrons. And we can compare that to our pot of valence electrons. Carbons are 4A, so they each bring 4 electrons. The hydrogens are all just 1 electron each. So you'd be adding all these up. Nitrogen is 5A, so it brings 5 electrons, and oxygen 6A, so it brings 6 electrons. All right. Let's go binary. I don't know. I think I missed something, but I guess it'll have to be missed. Just look at your sheet carefully. 2 types of mixtures. So we have homogeneous, well mixed, heterogeneous, chunky. Properties of mixtures. Let's see. Properties of mixtures is that they can be separated physically by physical means. And then also the other thing is it can vary in composition. Those are the 2 big things, I think. I think that must have been on a slide that I didn't bring in. Properties of mixture solutions. So properties, oh yeah, here it is. Each substance, as it's separated out, will keep its own identity. They can have different compositions. Can be separated by physical means. All right. So we have different types of solutions. Your solution can be unsaturated in that actually it can take more solute dissolved in. It can be saturated, and this is where I say you have a sludge at the bottom. And then coming up on the next slide, it can be what's called supersaturated, in which you have dissolved more solute in the solution, excuse me, than it really ought to be there. So let's see, what else do I have? Solutions, unsaturated, saturated, supersaturated. So this would be unsaturated. So, well, I don't know. Actually, this is all supersaturated. So what they're saying is this is an unstable supersaturated solution right here, and they're what we call seeding it, and it's growing these crystals. So this is saturated. Sorry, no, this is unsaturated because no sludge. There is sludge, so that's saturated. All right, what else do we got? What else do we have? Parts of a chemical equation. So noted there's reactants on the left and products on the right. Know that we use these symbols like an S for solid, L for liquid, G for gas. AQ means dissolved in water, aqueous. Then you are going to have to balance equations. So stoichiometric coefficient here is 1, 6, 4, 1, 2, 1, 2. And where I have those lines, when you balance them, that's the only number you can mess with. You cannot mess with the formula. You leave the formula alone, okay? But like as we balance them, we need to get the same number of atoms of each element on both sides, and we'll know it's balanced. So conservation of matter says that matter cannot be created or destroyed in ordinary chemical reactions. We kind of count on that. So again, this is the one that we did in notes, where if you have 3 Fe's, 4 H2O's, 1 Fe3O4, and 4 H2s, then you have the same number of atoms of Fe, H, and O on both sides of the reaction arrow. So I have endothermic versus exothermic reactions. So here we have a reaction that is giving off heat. So this would be getting hot. Okay, and giving it off heat we call exothermic. And this one, can you see the arrows going in? So actually this is what we call endothermic, and your solution would be getting cold. Good. So on to part 6, what is a mole? Well, a mole is 6.022 times 10 to the 23rd of anything. So that's called what we call Avogadro's number. So you are going to have a few problems. Oh, goodness, excuse me. You can have a few problems on the test, not as many as their physics test. So, and no problems on astronomy. Yay! So in this case, we have a sample containing this number of atoms, and how many moles are there? So what I usually do is I say 1 mole is equal to 6.022 times 10 to the 23rd, in this case atoms. And I'm going to use this equivalency statement. I'm going to turn it into like a ratio to work my problem. So 3.011 times 10 to the 23rd atoms, I usually put that over 1, times, and I want atoms to cancel, so I'm going to put atoms down here, and I put moles here. And so I have 1 mole here, and I have 6.022 times 10 to the 23rd atoms here. Now, on your test, I need you to show the work. Now, if you just simply take this number divided by this number, which is what I ultimately do, just show your work, and then you're going to be great. You'll be golden. In this case, how many moles of carbon atoms are there in present? Wow, that many moles. So if we have 5.45 times 10 to the 24th moles, how many atoms are there? So in this case, 5.45 times 10 to the 24th moles. That's a lot of moles, by the way. And then I'm going to go 6.022 times 10 to the 23rd atoms over 1 mole. So in this case, I'm going to what? Multiply these two together. Okay. All right. So let's see. Definition of molar mass. Units. Molar mass, by definition, is the mass, grams, in 1 mole. Okay. So units of molar mass are grams per mole. So the molar mass for the elements, all you got to do is look up the periodic table. So I happen to have one handy. So KRF krypton, of course, is one of those noble gases in 8A, and its decimal number is 83.80, and that's also its molar mass. So 83.80 grams to get 1 mole. Okay, so etc. Then I have extra credit. Given the mass of a specific element, how many moles is this? So if I look up silver, I can find MM, or the molar mass of silver, is its atomic number 47. I found it. So its decimal number is 107.87, and that would be grams per 1 mole. Just for silver. So to work this problem, my first term is going to be 7.9 moles. I'll put it over 1. And if I want moles to cancel, I won't flip it. I'll just bring it like as is. So 107.87 grams per 1 mole. Now moles cancel and we're left with units of grams, and that'll be our answer. Now this one, it's a different element, so I need to look up the molar mass of bromine. And bromine is a halogen, 7A. And its decimal number is 79.90 grams per 1 mole, just for bromine. So in this case, this is going to be my first term, 0.0041 moles over 1, and this is just for bromine. So can you see where this time I want to use this information, but I want moles to cancel, so I'm going to, flip it. So I'm going to put 1 mole over 79.90 grams. That's just for bromine. Did I do that right? Huh. No, I didn't do that right, Drat. I bet you caught that at home, didn't you? So if I want moles to cancel, I'm going to use the unflipped version. Sorry about that. So it threw me off because it's just like the one at the top, 79.90 grams over 1 mole. That's the molar mass of bromine. I must have, here's the other type of problem. So also for extra credit, if we look up helium, a different element on the test, but the decimal number for helium is 4.003, and that would be units of grams per mole. That's for helium. So in this case, I'm going to try to go from 5.6 grams to moles. So that 5.6 would be my first term. And I'm going to use this to my advantage. And now can you see if I want grams to cancel, I have grams in the numerator here, so I have to flip it. So for helium, 1 mole will weigh 4.003 grams. And now my grams will cancel and be left with units of moles. So I'm done. And then this one's just like that. So I hope this has helped. The one thing, like I said, I didn't, and I'll just go ahead and do it on this last slide if you'll bear with me. I have up here for simple binary ionic compounds, write formula and name. So for instance, if I told you I wanted to make something that had calcium and it also had, let's see what would be a good example, calcium and nitrogen in it, okay? I want to make an ionic compound. Of course, calcium is a metal and nitrogen is a non-metal. So I definitely have an ionic compound here. So what I need to do is find calcium on the periodic table, and what you probably have written above that column, 2A is a +2. So calcium is going to form a +2 charge. Nitrogen above the 5A elements, the non-metals anyway, you have a -3. And I called it crisscross before. So the number of calciums I need is going to be the number on the of the charge on the nitrogen. So I'm going to do 3 calciums. The number of nitrogens I need is the number on the charge of the calcium. So I need 2. There you go. So that's crisscrossing. So that would be what I call the neutral formula unit. I'll show you the check. So 3 times +2 plus 2 times minus 3, of course that's equal to 0. That makes it neutral. So now to name this, I'm just going to give it the first name, calcium. And then the last name, instead of nitrogen, I have to lop it off and end with IDE. So it's nitride. So be able to do that. I think that's it.